So welcome everyone back to day 2 of the AI Surrey Summer School. And just in case you're on Twitter, we have a hashtag that we're using for today, which is just simply AI Surrey Summer School, one word. So this morning I'd like to introduce John Collomosse, who's going to be introducing deep learning. So John, over to you.
Okay, thanks Mark. Good morning everyone. Thanks for getting up early to come to the talk. So I'm excited to share with you an introduction to the topic of deep learning this morning. How many people have heard of deep learning? Heard the phrase? Oh, quite a lot of people. Okay, great. Okay, so for those that haven't, so deep learning is all about using complex neural networks to perform machine learning tasks. So getting machines to make decisions, to spot patterns in signals. I'm a researcher in computer vision. Been working in computer vision for over 15 years now, and really over the last 5-6 years, deep learning has just completely transformed the field. And enables us to do things that we couldn't dream of before. The sort of tasks we're performing with deep learning now are really eclipsing the performance of past methods by an order of magnitude. I'm going to talk a little bit about the kinds of applications that we see of deep learning, particularly in computer vision this morning. I'm going to give you an overview of how some of those deep learning techniques work. I hope you'll join us for the lab after the coffee break, where you'll be putting some of the techniques I cover in the talk today into practice. Okay, so I'll start off with a couple of examples of deep learning. If I were to ask you what all of these people here have in common, the hints at the bottom, the answer is actually none of these people exist. Okay, so all of these photographs have been synthesized using a technique called style GAN. A GAN is a kind of deep learning neural network. Someone has rigged this code up to the website thispersondoesnotexist.com, and every time you visit this website, this neural network is activated and generates one of these images. And I guess these I hope you'd agree, would be very realistic photographs, but in fact completely synthetic. Another really exciting application of neural networks, and again GANs, is in the use of creative technologies. So here on the left-hand side, we have a user drawing just a simplistic diagram using different colors, each color corresponding to a different kind of object, what we call a semantic class of object. And on the right, there's a photograph of a natural scene being completely synthetically created by this GAN network. And again, this is work from NVIDIA, some work called GAN that came out this year. So really useful application here of GANs as a creative tool. So we're going to talk about lots of different kinds of deep learning technique and neural network this morning, and we will talk about GANs as well. Let me just start by just giving you some context. I talked about computer vision and how I've been working in this field for some time. If we're talking about computer vision, state-of-the-art computer vision around about 2012, it was considered quite a challenging task for a computer vision algorithm to look at a photo such as this cup on the left-hand side and say, that's a cup. Okay, it sounds like a trivial task to a human, but actually it's actually very challenging. And around about 2012, we had a data set available to us called ImageNet that had 1,000 different types of object in it, millions of images, 1,000 different types of object. And we could look at that data set and figure out the correct object 9% of the time. Okay. Now let's just fast forward just a few years, because 2012 was really when deep learning started to come on the scene. If we look at what deep learning can do in computer vision just 3 years later, we can not only recognize objects in images with superhuman performance, but actually we can start reasoning about entire scenes. We can start asking the machine to describe a natural scene in words. And we can even ask the machine questions. We can show the machine an image, say who's wearing glasses in this photograph, and then we can get a natural language response back. So this is really just demonstrating the step change in performance that deep learning has delivered to computer vision, and why it's such an exciting field to be in at the moment. Okay, so really the computer vision community, started to take notice of deep learning in this talk delivered at ECCV, which is the European Conference on Computer Vision, one of our big computer vision conferences, by Alex Krzyzewski, who proposed a network that's come to be known as AlexNet after his name. He demonstrated really double-digit performance increases on this ImageNet data set that I mentioned, going from just single-digit performance to, tens of percents performance, and very quickly up to about sort of 60–80%. So, and this is all due to the introduction of this concept we'll talk about later called a convolutional neural network to object recognition. And very quickly, lots of other computer vision researchers picked up on this technology. They started building it into all sorts of other algorithms. And this has really transformed the field. Around about 2011, you went to a computer vision conference. There'd be hardly any papers there on neural networks. You go to a computer vision conference 2014, 90% of the papers were on neural networks. So it really kind of shows the transformation that we saw. So what's driven this transformation, really? Several things. We'll talk a bit more about them on the next slide. Primarily, it's the availability of big data. Okay, so the availability of very large data sets like ImageNet, a data set of 16 million images, 1,000 different types of objects in that data set, and also the availability of compute power to train the neural networks. So here we have a server that we use in our research center on the right-hand side. You can see in there it has 4 GeForce GTX components. Those are graphics cards that people traditionally use to play computer games at high speeds, high frame rates. But actually what researchers found around about 2012 was that you could repurpose the parallelism in those graphics cards that most commonly was used to just render lots of pixels at once on the screen. You could use that same power to train complex neural networks, and that really unlocked the sort of performance benefits that we see. Here in the bottom left is a schematic diagram we'll return to later. This is actually a diagram of AlexNet, that network that Alex Krasevsky proposed in that talk, which really catalyzed this transformation of computer vision towards deep learning. So the challenges then for this kind of network, as I say, we'll come back to it, this thing called a convolutional neural network, or CNNs, around about this time was, well, you know, they were data hungry. People had actually known about these types of neural network for many years, but it really wasn't enough data around to train networks that had sufficient complexity to do anything useful. When we see things like ImageNet arriving, then people suddenly began to have the data available to train these networks. I mentioned processing power as well, but also really, and this is kind of the case across most research really, techniques sort of bubble up on the periphery of your fields. No one really pays them very much attention for maybe a decade or so, and then suddenly people become aware of them and jump on board with them and start researching them in large volume. And this is what happened with these convolutional neural networks. In fact, convolutional neural networks, this kind of deep learning, have been around since the early 90s in the field of optical character recognition, a field that most of us in computer vision thought had been solved, right? This is where you kind of look at a page of text and figure out what the characters are on a page of text. I certainly remember myself as a reviewer for conferences, sort of seeing the call for papers for a conference and thinking, oh, are we really accepting papers still on optical character recognition? But it's just as well we did, because if we didn't, then this kind of work would have been extinguished and maybe we wouldn't have seen CNNs today. So that's a kind of a lesson in sort of research diversity there. Okay, so let's talk a little bit about then what a deep neural network is. And I'm going to start by talking about what a classical neural network is. So these are the kinds of neural networks that were very popular in the late 80s, early 90s. What the technical term for them is a multi-layer perceptron, or MLP. Okay? So when people were using these networks to perform image classification, basically figuring out what it is in an image, then what they would do is they take all the pixels of an image, and in this case we're assuming we've got a grayscale image, so like a black and white image. We stretch all those pixels out into a big long line and present them to the input nodes of a neural network. So a neural network is made up of lots of these nodes. We call them neurons, and these nodes are connected to one another, so in layers. So we have the first layer, the second layer, in this case an output layer in the network. Now each of these neurons is accepting inputs from all of the neurons in the previous layer. Okay? So what happens is the pixels get presented to the first layer of the network, and then signals from those neurons are passed into the second layer of the network, where they get kind of combined together in some way. Let's talk about that in a moment, and subsequently get then passed forward to later layers until we reach the end of the network. And at the end of the network, some numbers get output, which hopefully look like probabilities corresponding to how likely it is that object contains different kinds of object. So in this case, let's say probability of a dog, a cat, or a zebra being present. Okay? So what happens inside one of those neurons? Well, it's a very simple process. What's happening is all the inputs from the other neurons in the previous layer are being added up, but they're not being added up with equal importance. They're being weighted. Okay, so the neuron has some weights inside it, which are just numbers that correspond to how important the input is from each of the previous neurons. We call that a weighted sum, or weighted average, you can think about it as. Okay, they get added up together with another number called the bias. We don't really need to worry about that. It's just a constant number, and that number, that sum, is then passed forward to subsequent neurons in the network. It gets passed through a function called a sigmoid function. Okay, that function basically takes the numbers which could be in the range negative infinity to infinity and just squashes them down into the range 0 to 1, what we call normalization. Okay, so that is all that's going on inside a neuron. So hopefully you can see that the behavior of the neuron is entirely defined by the values that are given to these weights inside the neuron. Therefore, if we want the network to behave in a way that is sensible, for example, gives us some sensible numbers out of the output layer, we need to figure out what the right set of weights are for every neuron in that network in order to get it to do the right job. Does that make sense? Okay. By the way, I just want to say at this point, if you've got any questions about anything, just stick your hand up. I'm happy to take them throughout the talk. We'll do questions at the end as well. Okay, so when we build our neural network, and it's down to us as the human to design the structure of that network, what we call the architecture of the network, we just initialize those weights with random numbers. Okay, numbers we pull from a normal distribution or from a Gaussian distribution. Okay, and that means that if I feed an image into that network when I've just initialized it, I've just built it, what I'm going to get out at the end is obviously just going to be just garbage, right? Because it's just random numbers, okay? But anyway, let's talk about how that would work. We would take our image, we stretch its pixels out, we push it into the first layer of the network, the input layer. It goes then through this second layer. This layer has a name, it's called a hidden layer because it's not an input or an output layer, okay? And then gets pushed through and ultimately these numbers get spat out. We call this a feed-forward pass of the network because we're feeding an image forward through the network. Sometimes we call it doing inference on the network. There's a lot of jargon in this field. I do apologize for that in advance, okay? So, yeah, the output of this network is going to be bad. Okay, how bad? Okay, well, we use a mathematical function called a loss function, and I think this was touched on possibly by Shirin yesterday in her talk, to figure out how bad the network is performing. Okay, so the way that we calculate this is by looking at what we would ideally like the network to output. Ideally, if we put a picture of a zebra into this network, we would like the probability of zebra coming out to be 1, and the probability of all the other classes, that means types of object, coming out to be 0. Okay, so our ideal response is 0 everywhere and 1 for zebra. We call this a one-hot response for zebra. Okay, and obviously when we put our image into this initialized network, we're not getting the one-hot response, we're getting some garbage out. So what we're going to do is figure out how different that response is to the one-hot vector for zebra. This requires us to know what kind of object, of course, is in this image, okay, in order to assess this. And we call that the ground truth, the annotation for that image. So somebody has come along and said there's a zebra in that image, and that's caused us to generate this one-hot vector for zebra, which enables us to then measure how bad the response of the network is, what the loss of the network is, in other words, for that network, for that image. Okay, well, so what precisely is the loss function? There are lots of different forms of loss function for different tasks. A common one is the MSE loss, mean squared error loss. All we do is we difference the response with the ideal response for every output, square those differences, add them up, and then divide by the number of outputs, which of course is equal to the number of object classes, and that gives us our expression for the total loss of the network. Obviously, the higher the loss, the worse performing the network, and in an ideal situation, we'd like that loss to be 0. Does that make sense? Okay, so, right. So how do we then get the weights in this network to resemble something sensible, but to give us a network that performs in a way that minimizes this loss function? We have to do what we call train the network, okay? And we do this in an iterative fashion by updating the weights in the network. We sometimes call those the parameters of the network, in order to reduce that loss function. So what we'll do is we'll start with this final layer. We work backwards. So we start with the final layer, and we look at each neuron in turn, and each weight in each neuron in turn, and think, okay, if I want that loss function to decrease, should I be increasing this weight or decreasing this weight? Okay? If you want to think about it mathematically, what we're doing is calculating the rate of change of the loss function with respect to that weight. So it's like a first derivative of the loss function. We call it a partial derivative because we're just looking at the single weight there that's making a difference. Okay? That is then going to give us a decision as to whether to increase or decrease that weight. We then basically make that decision for all of the weights in that layer, and then we work backwards then through the network, updating each layer in turn. And this algorithm is called the backpropagation algorithm, and it's actually the fundamental algorithm that underpins training of any of the neural networks that we'll talk about today, either the classical type like this or deep neural networks. I'm not going to go into detail about how backprop works this morning. That would take about an hour in itself. But we just need to know a few things. We need to know that for each weight, we're basically calculating this derivative, the first derivative of the loss function with respect to each weight. The key takeaway message from that is that our loss function has to be differentiable. Okay? So that MSE loss function I showed you is, and there are other things like log loss and so on that are as well. Okay? Now, how do we go about training this process, this network? Well, we do it iteratively, as I say, over a series of iterations that we call training epochs. Another bit of jargon there for you, sorry about that. Okay. What we'll have is a whole set of training data, and for a neural network, typically we'll have thousands of examples of images in that training set. What we're going to do is run through each image in turn, presenting it to the network and updating the weights in the way that I've outlined. And once we've done that for every image in our training set, we consider that to be one epoch of training. Okay, we presented all the training data to the network and made those updates. Okay, so we also update the weights by a certain amount. We don't just increase or decrease them arbitrarily. We update them by basically the magnitude of this first derivative function I've talked about, and we scale them, the amount we update it by a scale factor we call the learning rate. Okay, so we'll come back to these terms later on. But basically what we want to see, and basically every neural network training package will be able to produce a graph like this. What we want to be able to see is the loss function for our training data, what we call the training loss, decreasing and plateauing over time, time being the number of epochs that we train the network for. Okay. Now, there was a sort of slight simplification of what I just showed you. What we actually we don't present one image at a time to the network when we train it in this fashion. Actually, what we do is we take our training data and we subdivide it into batches, sometimes called mini batches if they're small. Okay, and the batches are presented to the network, and we make updates to the weights for an entire batch of images. So what that means is, I'll take, if I had batch 1 that had a zebra, a cat, and a dog, and whatever in it, I would push those through a feed-forward pass through my network, calculate the loss for each of those images, sum up that loss, and then do the backprop with that aggregate loss for that entire batch of data. It's just a trick we use to speed up the training process, because there's quite a lot of training data usually when you're training up a neural network. If a batch is quite big, if we've chosen to pick quite large batches, usually we don't want to update the weights very much. So what we'd like to do is keep that learning rate small. But if the batches are small, in other words, mini batches, then the learning rate of the network is going to need to be high, okay, to get sensible updates to the weights. Is this all making sense so far? Okay. All right, so okay, training a neural network then. We talked about how we would look at a graph and hopefully see the training loss converge, as we call it, drop down to a low value and plateau. Usually when we train the network, we don't just have a training set of data, we have what's called a validation set as well. This is a set of data that we keep separate. We don't show it to the network when we're making those weight updates, but what we do is it's like a little bit of test data. We push it through the network through an inference pass, a feed-forward pass, to measure how well the network is doing as we train it. Does that make sense? So the training loss is being calculated from the training data that is being used through backpropagation to update the weights in the network. The validation loss is being calculated from this totally separate set of data that we've reserved and we don't use to update the weights. It's just monitoring what's going on. Okay? As we'll see in a couple of slides, this lets us make sensible decisions about how long to train the network for and things like this. What we'll usually see is that the curve for the validation loss is a little bit higher than the curve for the training loss, because the data, the purpose actually of all machine learning really is to make generalizations from data so that we can make sensible decisions on unseen data. Okay, so because the validation loss is unseen by the network in the sense that it hasn't been trained on it, usually the network will perform a little bit worse on the validation data than on the training data. Okay? Any questions so far? Okay, so I talked then about how we split our data set up into these different partitions. If I've got a data set, like maybe this data set here, which is the Stanford Cars data set, I would partition it up into a training set. I used to do the backprop. A validation set I used to monitor what's going on during the training. And then usually I have another set at the end called the test set, which is what I'm actually going to evaluate the performance on after I've trained the network. Okay? So when people talk about, oh, my network performs at, X%, they're running their trained network on the test data. And these partitions have to be kept totally separate, or we consider that to be cheating. Okay? All right. Okay, so what sort of issues do we see when training these networks? Well, a common issue we see is what's called overfitting. Okay, so overfitting is when we train a model, and I think you had that term introduced to you yesterday. Basically, this is what we're going to describe the trained neural network as being. It's a model that represents our training data. Okay, what we're trying to do is come up with a model that fits the training data well and generalizes well. But if we overfit our model to the training data, what that means is our model is not going to generalize well to unseen data. So let's imagine I was training up a classifier to detect frogs. Okay, I train it up on green frogs. I show it a blue frog, it says that's not a frog. That shows that our training data is not sufficiently representative of the problem we're trying to solve in the real world, in our test set. Yeah? So basically not having a representative training data is one reason we overfit data. Another reason, specifically relating to neural networks, is typically if we train a network too long, it will also overfit the data. Another problem we encounter is what's called underfitting. So a classic story about neural networks that I think pretty much everyone has to say when they introduce neural networks is a story about the US military in the 80s using neural networks to try and spot from satellite photos whether there were tanks in a forest, in the trees. Okay? So they thought, okay, we're going to use a neural network for this. We're going to use an MLP because that's all we had in those days. One day, we're going to take some photos of tanks in the trees. They roll all their tanks into the forest. They take an aerial photo. The next day, they got rid of the tanks. They take another photo. No tanks in the trees. Okay? And that's their two sort of parts of their training data, their two classes. And then they think, great, I've got a neural network now that will classify whether there are tanks hidden in the trees or not. But actually, it turns out their neural network hadn't learned that. It had just learned out whether to tell if it was sunny or not. Okay? Because the first day was sunny and the second day was cloudy. And this is actually quite common in machine learning. You'll find that the model tries to fit to the simplest explanation of the data, which in this case would just be like the average brightness of the data. Okay, so this is an example of underfitting because the training data has been conflated with another factor and has not been sufficiently discriminative to allow the network to generalize in the way we want it to. So when we're training our network, what we'll often see is the training loss drop down. Well, we won't often the training loss won't drop down at all. We'll have to play with the parameters. But if we're doing well, we see the training loss dropping down. But sometimes what we'll see is that the validation loss has not dropped down. Okay, and this is telling us that the network is underfitting the data. Also, what we commonly see is the training data loss will drop down, the validation will too, so we're looking good, but then the validation loss starts to shoot up again. And this is telling us that the network at this point is no longer generalizing well to unseen data. In other words, it's overfitted the data. So this tells us that we should have stopped training at an earlier epoch, which is usually not a problem because our library will usually save the state of the model for every epoch. We just go and find the one that worked well. But this sort of shows why the validation loss is necessary. Yeah, why having a validation set is necessary, because without it, if we just rely on the training loss, we can't tell if the network is underfitting or overfitting the data. Okay, right, well, so far I've just talked about classical neural networks, what we call MLPs. And for a long time, people thought that actually an MLP is all you need. Hornet came up in the early 90s with a theorem that proved that you could basically approximate any mathematical function with just one single hidden layer in your network. Okay, what we call a shallow network. There's not many hidden layers in it. Well, okay, it's a theorem, it is true, but because we rely on an iterative algorithm, a numerical algorithm to train the network, actually it's not possible to train a network of this kind to represent any function, to do any task that we might want to do. So although in theory a shallow network is all you need, because we rely on backprop to do our training, which is like an imperfect process, but the best we have, we need to actually design our networks to have many more hidden layers in order to make them sufficiently powerful to have models that represent the problem we're trying to solve. This then takes us into why we want to do deep learning. So deep learning simply is doing machine learning using deep neural networks that have a lot of layers in them. Okay? But contemporary deep learning is a little bit more than that, because contemporary deep learning doesn't use MLPs, it uses other kinds of networks where the layers in the network, the neurons of the layers in the network, do something else. Okay? And the networks we're going to focus on today are what we call convolutional neural networks. Those CNNs that I mentioned, Alex Krasevsky there presented in that initial talk that really kind of catalyzed computer vision. But there, just as a sort of disclaimer, there are other kinds of neural network that are used in deep learning. There are RNNs, recurrent neural networks, LSTMs, and so on. Like the audio people use these quite a lot. My talk is really focused on the computer vision, and we're going to focus on these convolutional neural networks. Okay, so what is a convolutional neural network? Sounds complicated, right? Well, it is a neural network that does convolution. Okay, so what is convolution? Okay, so we're going to first of all spend just 10 minutes talking about what convolution is so we all understand that, and then we're going to talk about how a convolutional neural network works. But we can consider convolution to be a general kind of image processing operation. Okay, a 2D convolution. Okay, so what is a convolution? Well, I'm sure we're all familiar with the concept of a pixel. Digital images are represented as pixels. Each pixel is a kind of the atomic unit of an image, a picture cell. And actually, an image, when it's represented in memory, we can consider to be like a 2D array full of numbers. Okay? If we ignore the fact we're dealing with color images and just pretend this is a grayscale image, then the numbers here on the right-hand side correspond to how bright a pixel is. 0 would be black, 255 would be white, and the other colors, so the other gray levels are everything in between. So when we talk about doing image processing on an image, what we're talking about is figuring out a way of manipulating the numbers in this 2D array. And this is what a convolution will do for us. Let's just think about a kind of one possible operation we could perform on this image. If I took this image and I established a little square window over some of the pixels in that image, and then looked at the numbers there and averaged them all together, just with a mean average, and then wrote the result of that averaging out into a new image, right on the pixel right in the middle of that window, yeah? I could do that and just sweep that window all the way over that image, performing that operation. What I'd end up with is another image with different numbers in it, right? What would that image look like? Can you guess? A blurry thank you very much. It would indeed look like a blurry version of the original image, okay? In technical terms, we call that a low-pass filtered version of the image, but let's not go into that. So, okay, so it would look something like this. If I had an image here of our Surrey stag, and this is an application of doing this kind of operation, maybe it's got some speckly noise on because someone took that photo quite late at night and I had a cheap mobile phone camera, okay, get some thermal noise in there. Then what we would do then, if we perform this 3x3 averaging operation, is we would blur it a little bit, it's true, but it would also reduce that noise. Okay, so it's a denoising operation. Okay, everyone following so far? So we took a window and swept it over the image, and at every location what we're doing is averaging the numbers under that window, writing out the average to the middle of that window in a new image. Yeah?
Sorry, why does it take away the noise in the image when you do the averaging?
Right, well that's a great question. Okay, so, all right. So there's a bit of maths called Fourier's theorem that tells us that any signal, 1D or 2D in this case, an image, is actually comprised of lots of sine and cosine waves of lots of different frequencies. So we can consider an image as having low frequency components and high frequency components. Now the blurring operation is a low pass filtering operation. What that means is it filters the image and only lets the low frequencies go through and blocks the high frequencies. Okay? Now high frequencies in an image correspond to kind of speckles or areas of the image where the intensity changes very quickly, like the Gaussian noise. So by applying a low pass filter to it, we're removing high frequency artifacts in the image, like noise, but also like edges, which is why it looks a little bit blurry. Okay. Okay, right, so another way to think about this operation, it's basically another way of saying the same thing, is I'm going to come up with a little window of numbers. Each number is going to be 1/9. I'm just writing it like this for shorthand, okay? And what I'm going to do is sweep that window over my image, and at every location I'm going to place for place multiply those numbers with the pixels underneath, sum up the response, and write that out into the output image to the middle location of that window. Does that make sense? And we do the little animation again. The window's sweeping over the input image, and at every location, that window is getting put on top of the image. The numbers are being multiplied together in correspondence, yeah, in place for place. The answers are being summed up, and the output, in that case for the first pixel, 4/9, is getting output into the output image. Yeah? Okay. This is exactly the same operation I just described, because by multiplying all of these numbers by 1/9 and summing them up, we're calculating the mean average, right? Everyone see that? Yeah? If I take 9 numbers, add them up, divide by 9, I'm going to get the mean of those 9 numbers. Yeah, that's what's going on here. Okay? I'm just talking about it in a slightly different way, a more general way. Okay? So this is a convolution. Okay? This process I've talked about, sweeping one window over, well, basically you consider this to be a little image. We're basically convolving this image, this small filter, with this actual image to produce an output image. Okay? That's a convolution. It's a kind of general image processing operation, because what we can do, and what we'll see, is you can stuff that 3x3 window with different numbers and it will perform different things. So we've seen the example of 1/9, that produces a kind of a blur. There are other kinds of blur we can perform with other numbers. We can get into that another time. We can do other things. We can do edge detection. If I take this image here, I can filter it with a couple of these filters, blend their results somehow through a magnitude operation, and get an output image. I can even sharpen up images. This first half of the image is the original, the latter half is the sharpened version, by convolving it with a filter that looks like this. So convolution is a general framework for performing filtering operations on images. Yeah? It can pick out low frequency artifacts, it can pick out high frequency artifacts like edges, it can amplify high frequency. It's basically pulling out different visual artifacts in the image depending on the numbers that are in that filter. Yes?
Do you have to reduce the data as you go across the image?
Yeah, so that's a great question. Thanks for asking it, because it's kind of important for later in my talk. yeah, you'll notice that the input image and the output image here are different sizes, yeah? So what's happening here is we're centering this image here on this 0, so the output is going to be here where this 1 is, but I couldn't center this window on the 0 here or the 4 here or so on, because it would go out of bounds of the image, yeah, go off the edge of the image. So that means that this region around the output image, what we call the invalid region, is making the output image basically a little bit smaller. And by the way, convolution doesn't have to be with a 3x3 filter. It can be with like anything that's odd numbered. So it could be like 5x5, 7x7, 11x11, whatever. And that will increase the size of that invalid region and therefore decrease the size of the output image. So yes, that is always a problem with convolution. But as we'll see in a moment when we talk about convolutional neural networks, it's actually a good thing. Okay?
Why
Yeah.
does it have to be on?
Well, because you've got to center it on a pixel.
Oh.
Yeah. You couldn't center it exactly on a pixel, otherwise it would if it was even. Okay, last thing about convolutions then, now we know what they all are. Okay, one of the interesting properties of convolution is that it is associative. Okay, so if I have an image here, like this grass image, and I apply a blur operation to it, maybe to blur it a little bit to get rid of some noise, and then I apply a second convolution, maybe with this filter, which we saw was an edge detecting filter, I'll get this output. But what I could do, because these filters are just images anyway, is I could just convolve these two filters together and then just do a convolution of this image with just a single filter to get the same output. We call this property associativity. Okay, we see it in like multiplication in maths as well, yeah? Okay, that's just like something to note, that two successive convolutions on an image basically boils down to just one convolution, yeah? Okay. Right, so finally, we get to deep learning, okay? Okay, so, as I say, we're going to focus today on convolutional neural networks, CNNs. And a CNN is a neural network with a lot of layers. This diagram here is the diagram of AlexNet. This is Alex Kraszewski's network that he presented at ECCV and also at NIPS that year. Okay, and we can think of the layers in this network not as being like the layers in a multi-layer perceptron, but as layers that perform convolutions. So each of these stages in the network, these layers in the network, is performing a convolution. The image is getting input on the left-hand side of the network, just like before. But then this first layer, we're calling conv1 here, is performing a convolution on that image and outputting another image. Now, in this diagram, you can see it has 11, 11 here on this little window, which is telling us that the network has been designed such that first convolutional layer is performing a filtering operation with an 11 by 11 filter. Not 3 by 3 like I showed you in the previous slides, 11 by 11. Yeah? The output of that layer is then getting fed into another convolutional layer, which is then performing a convolution, in this case with a 5 by 5 filter. And so on and so on and so on. And we'll talk about the end of the network in a moment. So does that make sense? So the convolution that's being performed here by this layer, the operation of that convolution is defined by the numbers in the filter, just like we saw it was here. Different numbers do different jobs. Okay? So the weights in this network, in this kind of neural network, are the numbers in the filter. They're the things that have to be learned. Yeah? Okay. Now, I've oversimplified again, because actually what happens in a convolutional layer is it doesn't just do one convolution, it actually performs several convolutions. So there's actually not just one 11 by 11 filter being learned in this layer. There's actually 55. Oh no, sorry, no, that's wrong. 96, in fact. Okay? Yeah? So an image is going in, 96 images are going out, each one different according to the filtering operation that's been performed. So you can think about this image going in as, because it's a color image, it's an RGB image, it's got like 3 grids of pixels basically. It's like a red, green and a blue stack. You can think of this as being almost like a 3-dimensional matrix. We call that a tensor, being height, width, 3 layers. Yeah? when it goes into the convolutional layer 1, 96 of these filtering operations are being applied to it. So we actually get 96 images coming out. Each of them's got 3 layers. So it's actually kind of 96 times 3 deep tensor. Yeah? Does that make sense? What will happen is that the image has shrunk a little bit because of that invalid region. This is why I was very grateful for you asking the question. Thank you very much. The image has got smaller, but the number of layers has got much, much larger in that 3-dimensional block of data that's moving through the network. Does that make sense? Yeah.
Do you have to apply the same filters to every color region?
No, but let's not go into that too much detail. It's not time. Okay. So you can see that this image, as it moves through the network, we're getting a block of data, 3-dimensional data. It starts as basically just a 3-dimensional block of data, but that is getting many more channels, many more layers. Again, more jargon, I'm afraid. Okay, as it moves through the network, but its dimensions, its width and height, are getting smaller. And eventually, as we get towards the end of the network, that image will be very small, but have loads of layers and channels. Okay, it might even be just 1 pixel big. Okay, so that's where we are when we get to the output of Conv5. That output then gets fed into what's called a fully connected layer. Okay, you can think of that layer as, well, basically being the same as the MLP layers I showed you before in the classical neural network. It's basically a classical neural network layer. So what we're doing there is taking the image and, just as before, stretching it out so all its pixels are in a big long line, and that will be very long because there's a lot of channels now. Okay, and just getting fed then through a layer of neurons, just like we saw those green circles in the MLP word, just classical MLP neurons. And we've got 2 layers of that before we get to the final layer, which is the output layer. And this network was designed to classify the ImageNet dataset, which has 1,000 classes in it. So our output of the network will have 1,000 nodes, yeah? Each one corresponding to the probability of a different kind of object being present in the input image. Okay, it's a lot to take in, I know. Let me summarize. This is a convolutional neural network. It comprises several layers. The layers perform convolutions on the image, which is like a kind of general image processing operation. The specific operation it performs is defined by the numbers, the values in the filter. We call those the weights of the network, analogous to the weights we saw in the previous type of neural network, the classical neural network. The image, as it passes through the CNN, gets shrunk down in its width and height until it becomes extremely small by the time it hits the FC layers. But it gets many, many more channels. And ultimately, the FC layers help boil down those pixels into an output, which is just 1,000 numbers, corresponding to the probabilities of the different objects being present. Right, any questions on that at all?
So if I've missed why it goes deeper, the number of layers?
Why?
Yeah.
You mean why do we have so many convolutional layers?
You say it goes
Yeah.
from a 2D image, that's effectively one plane, and then it
Well.
strips horizontally, vertically, and then goes down to many planes.
Yeah.
How is that happening? Is that a mathematical process?
Yeah. So you talk about the image as being like a plane. So yeah, you see how this input image here gets reduced in its size because of the invalid region of the convolution. So that's why the image gets smaller. The image, we get more channels because actually each of these convolutional layers isn't doing one convolution, it's doing 96 of them, for example, and just concatenating all of the outputs into a big stack.
Oh, I see.
Yeah? Any other questions? Yeah.
Are the blocks that are doing the convolution
Yeah.
on the left-hand side, are those also neural networks, or are they floating point processing units?
These things here. Yes, these, right, well, I'll unpack what that does in a moment. Okay, but in this slide, we're considering that to just perform a bunch of convolutions. Okay, right, yes?
We increase the number of convolutions to improve the performance of recognition. Like the more convolutions you perform, the more you have accuracy at the output.
Yeah, generally speaking, the more layers in a network and the more convolutions we perform, in other words, the more weights in a network, the greater its representational power and the more complex task it will perform. But there are complexities I'll come to with that in a moment. Okay, so what's going on inside one of these boxes, your question? Okay, again, I did oversimplify, I apologise a third time. Okay, because this box actually doesn't just perform a convolution, it actually does three things. I've called it a layer, but really, I should have called it a stage, because that stage, that convolutional stage, actually comprises three layers within it. What do they do? The first does convolution, we just talked about that. It's a convolutional layer. But then we have these other two layers, what we call a ReLU layer, which stands for rectified linear unit, we just call it ReLU, and a pool layer. And those triples of layers are so common in neural network design, CNN design, that we tend to just draw boxes like that when we refer to kind of all three of them. Okay? So a stage in that network comprises conv, ReLU, pool. Actually, you'll see in the AlexNet diagram, the first convolutional stage, let me wind back, the first convolutional stage, the second convolutional stage, and the fifth are conv, ReLU, pool. They have this max pooling, this pooling operation, but actually the third and fourth don't. So those are just conv, ReLU. Anyway. So what is the ReLU layer doing? Okay, well, ReLU actually turns out to be fundamental to a deep network's performance gain over classical or shallow neural networks. ReLU actually is a very simple function. It just looks at every pixel in the image, every pixel in every layer, and just, if it's a negative number, just clamps it to 0, just sets it to 0, and if it's a positive number, it leaves it alone. So we can consider the ReLU function, I don't know why epoch's written there, apologies, that's wrong. So if we've got x going into our function, the output of the ReLU function is just the same if it's positive or 0 if it's negative. Okay? Why are we doing that? Okay? Well, let's remember back that convolution is an associative operation. If I had an image convolved, that's what this star means here, with a filter A, and then I take the output of that and convolve it by B, it is the same as convolving with A, convolve with B, those two filters just boiling down to one filter, being convolved with the image. Yeah? That is then losing us the representational power of having multiple convolutional stages in our network, yeah? Remember, these convolutional layers in the network are learning weights, they're learning the filters. Okay? We want lots of them because we want a deep network that performs lots of convolutions to give us good representational power. If the conv layers just occur one after another, then mathematically, I could have 10 of them. I might as well just have one. It's the ReLU that introduces a nonlinearity between these linear filtering operations, separates them, gives the network its representational power. This enables the deep learning. Yeah?
And we don't have a negative pixel value after applying some filter, right?
You could have a negative pixel value because the weights that are learned, although in my examples all of the weights were positive, they could be, in fact, no, they weren't, because in fact I did have some negative weights there. In fact, yeah. So you could easily get negative pixel values.
Only after applying those you can have negative pixel values.
So this is a convolution. So our image is going in, it's going into conv1. Conv1 is a convolution. Now our output could have negative values going through the ReLU. Now it can't, and now it goes into the pool layer. So now we'll talk about that now. Okay. What's going on in the pooling layer? The pooling layer is a little bit like, it's not a convolution. It's a little bit like a convolution, okay, because it's sweeping a window over the image, okay. But what it's doing at every place, it's not doing any place-per-place multiplication. It's just calculating the maximum number and just outputting it to that center pixel. So it looks like a convolution, but it's a nonlinear operation, not convolution, okay. The max pooling layer is usually performs a kind of subsampling operation where we only take into account every so many pixels, maybe every 3 pixels, every 4 pixels. So this actually has the effect of subsampling, reducing the size of the image that goes through it quite dramatically. And the point of the max operation is to try and keep the activations, the signal as it passes through the network, rather than, say, an averaging under the window, which in fact would be a convolution. Okay, right. So Really, that's all you need to know to understand a CNN, that a CNN comprises these kinds of layers. Let me show you some examples of some CNNs. Let's start with a really simple CNN. This CNN comprises only a single convolutional layer, and what's more, it only has a single filter in it, so it's just learning a single filtering operation over that input image, followed by a max pooling layer, which is just basically subsampling the image to a low resolution. So I'm pushing this image through, which happens to be a video frame from a video I took at Chesington World of Adventures of a shooting gallery, okay? And then it's passing it through here, and what we're seeing here are the activations which corresponds, it turns out, to detections of the little targets there. So there's the video on the left-hand side, and there's the output. Oh, sorry, that's not true. So there's the input on the left-hand side, and then the little stars I've put on bright areas on white pixels that have been output by the network. So you can see it's done a reasonable job at detecting the target positions. On the right-hand side is the training data that I used to train this network, to learn the filter, that single 7x7 filter, in fact, as it was. Okay? So there's only 49 weights in this network, but still it has managed to learn with just 50 images how to detect the targets in this input image. Yeah? Just flip back to the schematic, much as it is a schematic. It's a convolutional layer with a 7x7 filter and followed by a max pooling layer. So, no, this is really quite exciting, I think, because in the past, in classical computer vision, we'd have been running edge detection on this image. We'd have been looking for little texture patches that look a bit like targets. We'd have been, doing all sorts of manually designed operations. But actually, we can just show this simple network, this data, and have it learn a performant model with just a minimal amount of training data. Let's look at a slightly more complex network, and this is actually one of the first times the CNN appears in the literature. One of the first times. There's a lot of work by Jeff Hinton. So this is a network called LeNet, after Jan LeCun, who is now the director of Facebook AI. And basically, he was one of these early proponents of CNNs back in the early 90s. And he was using CNNs to recognize handwritten characters, handwritten digits. Have a look at the diagram from that paper all that time ago and how much it resembles what we're using now for CNN. We've got an image going in, we've got a conv layer, a pooling layer. So we've got conv value pool, a couple of fully connected layers, and an output. It's like a super short version of AlexNet. Okay? Now, at the time, we didn't have the data to train networks that are more complex than this. We didn't have the compute power either, but now we do. We have much deeper networks that can perform object recognition over much larger images with much larger number of object classes. Okay, so just to summarize then, this is the AlexNet CNN, this object recognition CNN from 2012. The image goes in, it passes through convolutional stages, each of which comprises a conv, relu, and pool layer. Some don't have the pool. Then goes into a couple of fully connected layers, which are just like those MLP layers. And then on the final layer, actually we do a little bit of normalization because the numbers that come out of this tend to not sum up to 1, so they're not really probabilities. We call them logits, or you can consider them to be likelihoods. But there's a function called softmax, which is just a way of normalizing that. We don't have to worry about that today. So what is actually getting learned by this network at the different stages? Well, if we were to look at the filters inside the layers, we would get some understanding as to what kind of visual artifacts are being picked up at each stage. At the very first stage, the first convolutional stage of the network, we're learning filters that look a little bit like this. Now, we don't have time to talk about it today, but these basically are filters that resemble edge detection operations. They're called steerable Gaussian derivatives, first and second derivatives of Gaussians. Middle layers of the network are firing in the presence not of edges, but of collections of edges, of high-frequency artifacts that resemble different textures. Okay? And then as we move to later layers of the networks, they're firing on collections of textures and edges that resemble subparts of objects, like dogs' noses or hands on a clock, so things like this, and eventually to entire object classes. Now, these images here have all been generated through a process I'll describe in a moment. Basically, we can reverse the neural network and get it to hallucinate an image that will activate different bits of the network. So what we're doing here is activating different parts of the network to generate these images, to show what kind of things the network is looking at. And this is one of the ways, and I'm not going to go into it in too much detail, I've got a few slides, but I know Chris Russell will talk about this afternoon. This is one of the ways we can explain the behavior of a neural network that's been trained. Okay, so AlexNet, that was 2012. Obviously, we're here 2019. We can do a lot better. How do we do better? Generally, we do it by increasing the number of layers in the network. Very soon after AlexNet, we had the VGG network, developed out of the Visual Geometry group at Oxford. And that VGG network, I think, was published 2014-15. You can consider it as just a sort of stretched out version of AlexNet. Instead of 8 layers, it's got 16 layers. And in fact, there's a version of it with 19 layers as well. Okay, but basically, you see the structure is just the same. It's convelu or convelu pool. So we basically got these stages of the network. Some have max pooling, some don't. Basically, all it does is instead of reducing that image quite rapidly, as AlexNet did, it's a more gentle reduction as it passes through the network, because there's 16 layers to get through rather than 8. Okay? It's a deeper network, and it performs considerably better than AlexNet. Here's a diagram of it. In this case, the diagram, I've simplified it, so instead of having 16 layers, it's 8, but it does have 16. It's just the networks that don't really change that have similar geometry. Sorry, the stages that have similar geometry I'll just drop from the diagram for brevity. Okay, so, well that's great. Well, we can just wait for graphics cards to get faster and faster and just make longer and longer, deeper and deeper networks. And then, ultimately we'll, I don't know, reach a singularity or something. Well, no, okay, doesn't work. Because the deeper we make our networks, the harder they are to train. Remember, we rely on this algorithm backpropagation to backpropagate these changes to weights, what we call the gradients, in other words, delta loss function, delta weight, back through the network to update the weights in it. And if our network gets too deep, then by the time we get to these earlier stages, the gradients are so small that they don't update the weights at all, and we can't train the network. So there are various tricks that we have to play, adaptations, if you like, we need to make to the training process in order to train deep networks. Some of the best performing networks these days, like ResNet, have 152 layers in them, and there are some quite clever things that go on there with skip connections and so on. So we won't dwell on this, but it's just a note that it isn't just a case of making networks deeper and deeper. Okay, so let's talk about some software frameworks that you might encounter that allow you to use these sorts of innovations, because you don't have to design it all by hand, implement it all by hand. The very first library, or one of the very first libraries that came out, was Caffe. This was developed by the Berkeley Computer Science Department, and actually was concurrent with the work coming out from AlexNet. So in fact, some people call that network CaffeNet, some people call it AlexNet. But this is one of the original deep learning libraries. And I mean, again, arguably, is innovations like big data and also open source that have really driven the development of deep learning, because all of these libraries are open source software, and that kind of sharing and collaboration is as much a part of deep learning's history as the technology. We also have PyTorch. Now, arguably, PyTorch is probably the easiest to use library at the moment, probably the easiest to learn if you're getting into deep learning. It's developed by Facebook, and I mean, for a while it's kind of PyTorch, TensorFlow. I would say more people tend to be getting into deep learning using PyTorch now. TensorFlow is Google's version. It is a little bit harder to learn, but it is a lot more flexible. In the lab this afternoon, you get to try out PyTorch and TensorFlow in some hands-on examples. Keras is not a deep learning framework, but it's something that sits on top of other deep learning frameworks, particularly TensorFlow, to make it a little bit easier to use. And in fact, in the latest TensorFlow, which is still in beta, TensorFlow 2.0, there's kind of Keras built into that to try and make it a bit easier, so maybe arguably a bit more competitive to PyTorch for people learning deep learning. There's some other ones too. Okay, so great. Well, CNN's going to solve all our problems then, at least for visual recognition. Not really. Okay, they do have some disadvantages as well. I've mentioned several times that CNNs are data hungry. They have millions of weights to learn. AlexNet, as I showed you there, 2012, that had 65 million weights in it. Okay, so a lot of weights to learn. That means that we're going to need a lot of data to train the network. There are applications in visual recognition and other forms of machine learning where you don't have that many training examples. If you are doing some sort of medical image analysis where only 10 people in history have had that medical condition, have produced that scan, really you're not going to be able to use deep learning for that, okay? At least for the totality of the solution. CNNs are also very slow. Although running inference, a feed-forward pass on a CNN, is very fast, can be done in order of milliseconds or tens of milliseconds, they're very slow to train. It can take days or even weeks to train a network. So for applications where you need to do online learning, like if you had a robot or something that had to kind of adapt its machine learning, learn about the environment on the fly during deployments, right now it would be difficult to use deep learning for that due to the, how slow it is to train the networks. Explainability. It's very easy to measure how well a CNN performs because you just run some test data through it and figure out how many times it got it right. Okay? That's measuring the accuracy of a network, but it's much harder to explain why it is performing the way it is. And as I say, Chris Russell will talk a little more about that this afternoon. Another interesting thing about deep networks is actually, although we can sort of pretend, and the media likes to do this, that it's a neural network and it's a bit like a brain and it's seeing things the way the world is seen through human eyes, it's actually very different. The brain is asynchronous, it has things operating in parallel, the connectivity is highly irregular. Certainly each neuron in the brain is not performing a convolution in the way we've described it here. And consequently, CNNs don't see the world the way we see it. And I'll show you in a moment how easy it is to fool a CNN. I could show you an image that looks to a human like, an ice cream, but actually to a CNN it might look like a completely different object class. And it's quite easy to attack a neural network in this way. So there are cybersecurity implications here. Okay, right. So let's look at some things we can do with CNNs. I mentioned before that one way that we can explore why a CNN is performing the way it is to look inside at what the different stages of the network, the different convolutional layers and filters have learned. And one way to do this is to reverse the network, to put a one-hot vector in at the end of the network, for example for zebra, as we saw before, and figure out what the image is that will get us as close as possible to that one-hot vector. Okay, so this is a process we call activation maximization. We're trying to figure out the image that will activate the network maximally on that particular output pin for the object class that we're interested in. In other words, hallucinate me the ideal zebra. Okay, and actually you can get this network to hallucinate images that will activate any stage of the network, which is what I showed you before in that diagram with the different textures and so on. Okay. What is the value of doing this? Because we want to learn what the CNN has been trained to see. So this is an example. This image here, it was generated by Google a couple of years ago. It is generated from their deep network, which is called GoogleNet, but it's basically similar performance network to VGG network. And what they've done there is reverse the network in that way to hallucinate the ideal image for the class dumbbell, the weights that you lift down at the gym. Okay. Now what the network has hallucinated is not a picture of a dumbbell, it's of an arm attached to a dumbbell. What does that tell us? It tells us that the training data was biased. The training data didn't contain pure dumbbells. For the most part, it contained arms holding dumbbells. Okay. What does that mean? It means that it won't generalize well to images of dumbbells that don't contain arms. Now let's think of another scenario. Let's say I have an autonomous car in 10, 15 maybe years time, and it's driving down the road, and it's driving down an urban street, and it's got pedestrian detection algorithm being driven by a CNN. Highly plausible scenario. Okay. Maybe it performs really well in that urban scenario because it's been trained on a data set of pedestrians in an urban environment. But now, if I drive down a rural road, a country road, and there's a pedestrian there walking down the road, maybe it doesn't perform so well, okay, because it's not been trained on images of pedestrians in a rural context. How could we detect that bias in the training data using this kind of technique? Yeah? We can hallucinate the ideal pedestrian image, And if we see a high street behind them, we might know that it's a little bit biased towards urban scenarios rather than rural scenarios. So this is quite a useful debugging aid in detecting bias in training data for this kind of network. Okay, so how do we do this hallucination? Well, what we do is, as I say, we come up with this one hot vector for the class we're interested in. And what we're going to do is feed into our network. Remember, this network now has been trained. So this is a trained up AlexNet, say, in this example. I take an image, just a pure noise, white noise, which basically means noise sampled from a normal Gaussian distribution, and I feed it through the network to get the answer, which is kind of the probabilities of all the different classes we train the network on. So obviously this is just going to be meaningless. It's going to be a bunch of just random numbers. I'm then going to difference that response with the ground truth in a standard way using that loss function, and then backpropagate gradients through the network just like standard backpropagation, but I'm not going to update the weights in the network. I'm going to keep them fixed. I'm going to take those gradients all the way through the network and actually update the pixel values that are going into the network. And I'm going to do that iteratively. And if I do it iteratively, what I'll find is that structure emerges in the image, and eventually something like that dumbbells image will occur if it was a one hot ground truth vector for dumbbells. Let me show you this video. This is produced by a Google software package called Deep Dream. What's happening here is they are performing this activation maximization process to hallucinate ideal images for a one hot vector for dog. Instead of feeding in a pure white noise image to the network, they're feeding in a video frame from a guy who went down Walmart with a video camera, okay? But they're adding noise to it and then feeding it through this process. So what we see is that structures in that original video that perhaps slightly resemble dogs in terms of their edge structure and so on get kind of amplified and turned into dogs, and it's a little bit kind of trippy, but it's quite interesting to see the creative applications as well for this activation maximization process. Let me show you how the same process can be used to attack a neural network. In other words, make a neural network see things that aren't there. If I take this image and pass it through, again, I use AlexNet as a convenient example because it's short enough to fit into my slides. Okay, and that's going to give me, a sensible output like probability of a dog, probability of a cat being relatively high. What I can do is perform what's called an adversarial perturbation, make small changes that are very carefully crafted to that image to generate a new image, the image here on the right, such that that image, when fed through the network, will give me the probability of some arbitrary class I've chosen, like plane, being super high, like 99%. But to a human, it looks just like an image of a dog and a cat. And again, think about this autonomous vehicle example. I could whack some sticker on the back of a lorry, and to a human it just looks like a pattern or a poster of something else, but to an autonomous car it looks like a pedestrian slams on the brakes, some sort of accident occurs. Okay, so it's worth thinking about how these techniques might apply in the real world. So how do we generate an adversarial image? So we call these adversarial images. Okay, well, I just used the same process. Remember before, when we were hallucinating the ideal image for a particular class, we picked a one hot vector for the class we were interested in. We do the same thing here for an adversarial image. Here I might have plane was my example, so I'm going to have a one hot vector for plane. I'm going to take my image of something else that I want to use as the attack vector. I push it through my network. I get a high response for the class it actually is, bleach bottle in this case. Okay? But now what I'm going to do is compute the loss by differencing that response against the one hot vector for the thing I want it to be, the plane. I'll backpropagate that loss, and actually and again I'm going to fix the network so that the gradients are forced to update the pixels in the image. Now what's going to happen is a change will be induced in that image that reduces the loss. In other words, that makes the network think that that bleach bottle is a plane. And this is this adversarial image work. So it's a slide from one of my PhD students, Tommy. Here's an original image of an ice cream. These are the responses through, I think, the VGG network. So you can see it thinks it looks quite a lot like an ice cream, maybe a conch shell, a few other things. But he then, not actually using that process, using something that he's just published, a different process, but kind of similar, he induced a change in this image to maximize its performance for wallaby. So that image to a computer looks like a wallaby, but I think you'd agree to us still looks like an ice cream. So these kind of covert attacks are quite interesting. Okay, we've got about 50 minutes left, so I'm just going to show you a couple of other kinds of network that I think are interesting because you're going to be looking at them in the lab as well.
Sorry, can I just ask on that last one? So
Okay.
you set the wallaby as in ground truth as 1 to be able to do that?
I believe that was the case. So there are two different ways of doing this. You can do what's called a targeted attack, where you do what I've just said, or you can do what's called an untargeted attack, where you do a one hot vector for the class it is, but then it's actually negate it, so you try and make it go to -1 instead of 1, which basically means try and make it look anything but what it is. But in this case, I think it was a targeted attack. Okay, well, how many of you have got an app on your phone that does this? Okay, you take a photo and transform it into the artistic style of a painting. So, for example, like the Scream. Okay, so this process is called artistic stylization, and it's another area of computer vision and graphics that's been revolutionized by deep learning. And there's some mobile apps that have made a lot of money out of doing this, like Prisma and so on. I'm going to show you how CNNs can be used to do this. So what we have in this process is a source image, a photo that you want to stylize. That's the input. You also have an input, which is the style image, what you want that to resemble, and then this is the output of the deep learning process. So how does it work? Okay, well, let's just introduce a bit of notation. We're going to call the source image P. We're going to call the style image A. And we're going to call our output X. And what we'd like is for the content, like the houses, for example, of P to be reflected in our output. So we want the output X to have the content of P, but we want it to have the style, the appearance of A. Yeah? If I introduce a function here, C, which means the content of, we want the content of X to equal the content of P. We want the style, my function S, of X to equal to be the style of A. Okay? So let's solve for X. Let's figure out an X that responds in this way. It turns out that we can do this using that VGG network that I described to you, this sort of slightly longer version of AlexNet. Do you remember I told you that the middle stages of the network learn the representations for like the texture in the object, and the later stages are more to do with the kind of semantic class of the object, what kind of object it is. Yeah, we're thinking back to that slide. So it turns out that if we sample responses from this network from a late layer, then that gives us a pretty good description of the content of an image. So our function C of P is going to pull out some responses from a late convolutional layer in this VGG network. I'm going to feed my image through it. I'm going to see what kind of responses are getting triggered, maybe around here in the network, one of the late convolutional layers. And I'm going to call that response C of P. To get the style of the image, I'm going to sample from the early to mid layers of the network. Okay, I'm going to call that response S. Yeah, so that's my function S. So if I want to get the content of my source image P, C of P, I'm pushing source image P through this pre-trained network. This is a network that's been trained already on something like ImageNet, and pull out C of P. I'm then going to get my descriptor, my signature, if you like, of my style image by pushing the style image A through the network and sampling from an early stage of the network. And now what I would like to do is come up with an image X, which is basically a version of P that resembles A. How am I going to do that? Again, using this activation maximization. I'm going to take that image P and add some noise to it, just like Google did in that deep dream. I'm going to push it through this network and obtain my S and my C from it. And my loss function now is going to be penalizing differences in the content of my X from the source image content, and penalising differences in the style of X from the style of A. And that is my loss function I'm going to minimise and backpropagate through that network, keeping the weights fixed, just as we did with adversarial images and the hallucinating the ideal image. We're going to do that to hallucinate changes to this source image that make it look more like A. And this K here is a parameter we as users set which varies the strength, the importance of this term. In other words, varies the amount of stylization that applies to the image. So we take our image P, push it through the network, take our image X, which is a version of P with a bit of noise on it, push it through the network, calculate our C of X and our S of X, calculate the difference between the C, between those of C of P and C of A. Oh, sorry, that should be S of A, apologies, respectively. So we pre-computed these two, figure out the loss, backpropagate, and update the image. And we end up with a stylized version. So here is that photo stylized in 3 different ways, the original style image there inset on the left-hand side. So in the lab this afternoon, you'll have a go at stylizing some images of your own using some code that does this. The last thing I want to talk about today is a GAN, a generative adversarial network. Okay? These are the networks responsible for those examples I showed you right at the beginning of the talk, where we had the person that doesn't exist.com and the creative tool. A GAN is like another kind of network. It's a CNN, but it's just the architecture's different, such that it comprises 2 stages. What's called a generator stage and a discriminator stage. The network is trained kind of in competition with itself. The generator learns to generate fake images, and the discriminator learns to tell the difference between fake images and real images. Okay? So the generator synthesizes the fake images. What happens is you put a short vector of noise, put some noise into the generator. It then spits out a fake image. And then you train the discriminator to tell the difference between those fake images and real images. And obviously for that, we need a collection of real images. Yeah? And there's a combined loss function that lets you train that network up such that the generator and discriminator keep getting better at their respective jobs, and therefore the output, which ultimately what we care about is how good this thing is at generating fake images, is that gets better and better, more and more realistic, in other words. So how do we train such a network? And again, there's an example in the lab doing this. We initialize our networks with just random noise, like we always do for the weights. And what we're going to do initially is have our generator and just lock the weight, so we're not going to change the generator. We feed some noise into our generator. It generates a fake image. The image is going to be rubbish because the generator was initialized with random weights. We're then going to show that fake image to the discriminator and real image. In fact, we show a batch of such fake images generated with different noise vectors and a batch of real images. The discriminator then learns to tell the difference. What is the discriminator? It's just a classification network, pretty much just like AlexNet, except of having 1,000 classes, it just has 2 classes, real or fake. So it's not detecting the kind of object in the image, it's just classifying the image as whether it is a real image or a fake image. So we generate a whole batch of these fake images from the generator. We've got a whole batch of these real images that we've got from our photo collection. We push them through the discriminator. We train it up as a classification task. That makes the discriminator better. We then lock the discriminator's weights and try and improve the generator. How do we do that? By putting some noise into the generator, having it generate a new fake example. That then gets classified by the discriminator in whatever state it was in. Okay? That decision may be good or bad. What we'd like the discriminator to do is detect that it's a fake image, but it might not, so the loss function is formulated in that way. And then we backpropagate those gradients from the loss function. The gradients go through the discriminator without changing the weights, but they update the weights in the generator. So the generator gets a little bit better at making images that fool the discriminator, because the loss function is reversed. So so I should say, so in this case, the loss function is in the favour of the discriminator. What we're trying to do here is penalise decisions the discriminator makes that are incorrect. So what we're trying to do here is, if we put a fake image through that, what we're expecting to do is some sort of MSE loss on fake. Yeah, we want it to tell us that it's fake. In the case here, what we want to do is have the discriminator tell us that it's real, because we want the generator to get better. Yeah. So here's an example of the Here's an example of some output generated by such a GAN, as we call it, generative adversarial network. This is one of the original examples of applying GAN to computer vision problems. It was trained on photos from the IKEA catalogue of bedrooms. Okay, so every image of a bedroom here you see is completely synthetic. And if you look closely, there are issues with the structure, like beds are missing legs and things like that. But it's quite reasonable. GAN technology is an area of rapid research in deep learning. GANs really only came on the scene in about 2014 with Ian Goodfellow's paper, and then really only applied to visual computing around about 2015 with papers like the bedroom GAN, Radford et al. But one of the most exciting innovations, I think, quite recently has been the cycle GAN, which came out of Berkeley. Cycle GAN actually is two GANs in one. What we have here is actually a GAN that, and I'll flip forward to a result first of all, a GAN that will transform an input image into an output image in a different style. So in this case, it's transforming zebra into horse, and it can go either way. How does that work? Well, it's a network that has two generators and two discriminators. G is a generator, and also F is a generator. Okay, dy is a discriminator for G, and dx is a discriminator for F. So what happens here is we take our image X, which might be a zebra, push it through the generator here to get Y prime. Okay, dy discriminates and tells us whether Y prime looks realistic or not. Okay, but then what we do is we try and unconvert it, like back from horse to zebra again, to get X double prime, and that is then penalised. So, and then we penalise differences between X and X double prime. So the network is learning how to transform one way and then back again, governed by this discriminator. And then obviously there's the other path through the network where we've got an image on this side, which is your Y. You're transforming it to X prime. X prime gets put back to a Y prime and governed, regularized by this this discriminator here. So the reason why I think this is really exciting is that the only thing we need to train this network is two sets of photos, one for each domain. So a bunch of zebra photos and a bunch of horse photos. They don't need to be somehow in correspondence. That would be impossible to have a zebra in exactly the same pose as a horse and exactly the same background and so on. So what we have is unordered sets, two unordered sets, a set of zebra, a set of horse, and that is all that's needed to learn how to make a transformation between a zebra and a horse. So this is the beginnings of what we call unsupervised learning. Okay, we're learning without a lot of annotation on our data, what we call supervision or ground truth. We're beginning to learn without that, and I think that's why this sort of work is exciting. Which brings me to the future, just some closing comments really. First of all, it's important to recognise we are in a hype cycle for AI. The media would have you believe that deep learning is going to take over the world. We're going to see Skynet, etc. Pick your favourite science fiction film. Right? Deep learning is not artificial general intelligence. Some people would argue it's not even a form of intelligence. It's just a way of learning and generalizing from your training data. Okay, it's machine learning. Okay, so we are a long way to go from this, and it's really a matter of belief as to whether you feel that I think it's possible, but some people don't. I think what we're going to see in the nearer term future is data being treated a lot more as a commodity. Right now, it's very interesting to see how our digital economy has been democratized through digital platforms. We have things like Uber, we have Deliveroo, we have all of these services that are built on digital platforms that have enabled anyone in our economy to be a content or service consumer, but also a producer. Okay, so it's kind of decentralized the economy in that way. But the platforms are still very centralized, and I feel that the data that is enabling those platforms, when that becomes decentralized, we're going to see some true democratization of the economy. I mentioned already that one of the most exciting trends in deep learning and machine learning at the moment is around unsupervised, sometimes referred to as self-supervised learning. Why is it so exciting? Because we have just so much data out there at the moment, but so little annotation. And most deep learning approaches, most machine learning approaches require that annotation to train. We saw that with the one-hot vectors and the ground truth. To be able to do machine learning without supervision is really going to unlock the power of all that data we have in our society. And the other thing, we're going to see people really pushing on in machine learning and deep learning is domain generalization. So we see some really exciting work coming out of places like OpenAI, out of DeepMind, where they're training machines using reinforcement learning, and which is something I haven't had time to cover, to play computer games. Why are they playing computer games? Why are we wasting all this money? We're not wasting it. Okay, we are in fact learning how to perform unsupervised. In most of their papers, it's unsupervised learning within a tightly constrained environment. It's a tightly constrained domain of a computer game. You can only press up, down, left, right. Only certain outcomes will occur within a computer game like Mario. Okay, to take those techniques from a sandboxed environment like that out into the real world, where there are so many actions we could perform and the world is so noisy, is a big leap. But it's something a lot of people are working on, and this push to generalize your learning frameworks to more diverse domains, to more general domains, is something that is going to be really important to machine learning in the future. But in the most immediate future, it's the lab in half an hour after your coffee break. And in that session, you get to try some of the stuff I've been talking about out. We've got 3 exercises there, 1 training a classifier, 1 doing some of this stylization, and 1 training up a GAN. And I hope you're going to enjoy that lab. That's all I've got to talk about in this session. Thanks very much for your attention.